In environments handling flammable liquids, waiting for smoke to reach a ceiling detector is a fatal error. By the time enough particulate matter rises to trigger a standard sensor, a volatile liquid fire has already expanded across the floor. The Fire Detection and Alarm System, or FDAS, is the technical infrastructure engineered to detect these specific hazard signatures and initiate a coordinated response in milliseconds. Every fire moves through 4 distinct physical stages. It begins with the incipient stage, releasing invisible combustion particles. Next is the smoldering stage, where visible smoke appears. This is followed by the flame stage, characterized by ultraviolet and infrared radiation. Finally, it reaches the heat stage, where thermal energy violently escalates. An HSE engineer's primary task is matching specific sensor technologies to these distinct signatures. You have to intercept the threat at the earliest possible stage and architect an automated response that outpaces the combustion cycle. Preventing catastrophic failure requires a system that mathematically anticipates the physics of a fire, aligning specific sensors with the combustible materials present in the facility. The entire sensor network routes back to one critical piece of hardware, the Fire Alarm Control Panel, or FACP. This logic processing center constantly monitors inputs, verifies system integrity, and commands the outgoing network. Because the system must survive the exact event it is detecting, the panel requires strict power redundancy. The primary source is a non-switched 120 or 240-volt AC circuit, dedicated entirely to the fire alarm. If that fails, a secondary backup of lead-acid storage batteries or local generators immediately takes over. When an emergency is verified, the panel activates primary output notification devices. These audible horns and visible strobes are engineered to operate seamlessly even during a total facility power failure, ensuring a universally understood evacuation signal. The system also accounts for human intervention. Manual initiating devices, like pull stations, are mounted near primary exit routes, so occupants can instantly trigger the sequence if they spot a hazard first. Even the most advanced sensor network is entirely useless without this redundant command center to process the data and sound the alert. Gathering that data requires capturing specific phenomena. Standard point smoke detectors wait for particles to reach them, using ionization for fast-burning fires and photoelectric chambers for smoldering ones. But this passive method is too slow for certain critical environments. Aspirating smoke detection takes an active approach. These systems continuously draw air through a network of sampling pipes into a highly sensitive detection unit. In spaces with high airflow, like data centers, ASD can identify microscopic incipient smoke long before a point detector would register a change. This diagram illustrates the strict placement parameters outlined in BS 5839 Part 1. The sensing element of a smoke detection device, specifically the photoelectric chamber, must sit between 25 mm and 600 mm below the ceiling to reliably catch the smoke layer. This chart displays temperature thresholds for heat devices. To prevent false positives, a fixed device's static response must trigger at no less than 29 degrees Celsius above average ambient temperature. Looking at the curve slope differentiates detector types. A fixed detector waits for that specific threshold. A rate-of-rise detector triggers upon a rapid temperature spike, reacting to the fire's sudden slope rather than gradual warming. But thermal energy is often too late a metric for specialized industrial risks. Where hydrocarbon fires can ignite instantly, facilities utilize flame detectors that monitor for ultraviolet, infrared, or multi-spectrum radiation signatures. A dual or multi-spectrum IR analyzer monitors distinct carbon dioxide emission bands and reference bands simultaneously. This dual confirmation approach allows the system to differentiate the characteristic flicker of an actual flame from severe background interference like welding arcs or direct sunlight. Precision detection requires mapping the exact physical footprint of the hazard directly to the spectroscopic or thermal capabilities of the sensor. Once a sensor triggers, how the panel locates the threat depends on the network architecture. Conventional systems group multiple devices onto a single geographic zone. If a detector activates, the panel only knows the general area, forcing personnel to manually investigate the zone to locate the fire. Addressable systems solve this limitation. Instead of a single zone wire, communication happens over a digital data loop. Every device is assigned a unique digital address, communicating its exact status in hex or binary code to the control panel. With individual addressing, the panel pinpoints the exact detector triggered, monitors sensitivity, and runs remote diagnostics. Addressable systems trade higher initial complexity and installation costs for absolute real-time situational awareness when seconds matter most. The FACP categorizes network status into 4 distinct signals. An alarm indicates a verified fire. A trouble signal indicates an equipment fault or wiring issue. A supervisory signal monitors the status of critical related systems, like a closed sprinkler control valve. Finally, an alert provides a pre-warning indication. These signals drive cause and effect programming. Using a Modbus card, the fire panel communicates directly with the building management system, translating a fire signal into an immediate, coordinated physical response. Depending on the program logic, a single smoke detector can tell the panel to trigger automated gas suppression, shut down the HVAC system to starve the fire of oxygen, ground the elevators, and unlock emergency access doors all at once. However, this automation creates intense operational vulnerabilities if the sensors are wrong. In the UK, fire services report that 41% of callouts are false alarms, frequently triggered by steam, dust, or aerosol sprays. The consequences are severe. False alarms breed occupant complacency, drain critical rescue resources, and result in substantial financial penalties under the Localism Act of 2011. Mitigating these events starts at the design phase. It requires strict sensor selection, like deploying heat detectors instead of smoke detectors in commercial kitchens, and rigorous biannual testing schedules under standards like BS 5839. A system that cries wolf destroys its own operational value. Deep integration with building systems demands zero false positives. Every theoretical concept must adapt to its environment. Data centers, for example, demand aspirating smoke detection. Passive detectors cannot outcompete the high-velocity HVAC systems cooling the server racks, making active air sampling the only way to catch incipient electrical fires. Conversely, petrochemical refineries require multispectrum IR flame detection. In outdoor areas handling volatile hydrocarbons, ignition is instant. The system needs to ignore sunlight and process heat, triggering suppression the millisecond a specific carbon dioxide radiation band appears. For sprawling hospitality structures like hotels, the primary threat is navigating hundreds of sleeping occupants. These require highly automated, fully addressable networks to pinpoint exact room origins and execute complex phased evacuation protocols without inducing panic. There is no universal safety solution off the shelf. The operating environment dictates the exact system design. Let's lock in the technical specifics. Question 1. What separates addressable from conventional? Addressable gives every device a unique ID. Conventional groups them by zone. 2. Where do you use ASD? In high airflow environments, like data centers. 3. How do dual IR detectors prevent false alarms? By requiring a match across multiple infrared wavelengths. 4. What are the BS 5839 limits for smoke detector placement? Between 25 mm and 600 mm below the ceiling. 5. What is the static response delta for a heat detector? No less than 29 degrees Celsius above average ambient temperature. 6. What is a supervisory signal? A panel alert indicating the status of a critical integrated system, like a sprinkler control valve. 7. Why use a UV-IR combined detector? It requires confirmation from both sensors to reject false signals. 8. What does a Modbus card do? It translates fire panel logic into building management system commands. 9. What defines a multi-sensor? A detector that monitors more than one physical or chemical phenomenon, like heat and CO. 10. What causes most false alarms? Poor maintenance, steam, dust, and aerosols. 11. What are the risks of false alarms? Complacency, drained fire services, and financial penalties. 12. What is the maximum ceiling height for a normal ASD system? 10.5 meters. 13. Why do point detectors fail in cold storage? Condensation and extreme temperatures block the sensors. 14. Give an example of cause and effect programming, detecting smoke to automatically ground elevators and shut down HVAC. 15. What are the dual power requirements for an FACP, a dedicated AC mainline backed up by storage batteries or generators? If this breakdown helped you prepare, hit the like button, subscribe, and share this with your engineering team. Check out the channel for more deep dives into HSE system architecture and technical job prep. Memorizing the answers will get you past the interview, but total, rigorous mastery of the physics and the hardware is the only way to safeguard human life in industrial operations.